Hi, it's Professor Davis here, and we want to talk about a topic that I find mystifies students at times. It's called Chebyshev's theorem. You usually see this when you are first introduced to measures of variability, sometimes called measures of dispersion, like the range and the standard deviation, when you start to take a look at some of those applications. And, a lot of students seem to struggle with this, but it's really a pretty easy idea. And let's just take a look at it and see how the applications in Chebyshev's theorem work. First, just in terms of history, there's Chebyshev right there, born in Russia in 1821. He lived before the Russian Revolution and lived during the time of Nicholas I. He has other contributions. One of them was he proved the law of large numbers. The law of large numbers states that as the number of trials of a probability experiment increase, the theoretical probability and the empirical probability we see by measuring converge to the same number. And that's an important theorem for probability theory. Now, he also became a professor, and he taught Andrei Markov. If you ever take finite mathematics, you'll probably have a chapter on Markov chains, and Markov was one of Chebyshev's students. Now, Chebyshev's theorem lets us know a lower bound, so to speak. It lets us know what the least we can say about a set of data would be. All right, in terms of its containment and its, not knowing anything about its dispersion. The theorem applies to both sample statistics and population parameters. So we can either use the sample mean and standard deviation, x bar and s, respectively, or we could use the population parameters, population mean mu and population standard deviation sigma. The Chebyshev's theorem is similar to the empirical rule, but it doesn't make an assumption about the way the data is distributed. All right? So let me show you what I mean by that with a little contrast here. Here's the empirical rule. Maybe you've seen that when you first talked about measures of dispersion. It tells us, for example, that about 68% of the data lies within one standard deviation of the mean, 95% of the data lies within two standard deviations of the mean. But notice, this makes the presumption that the distribution of the data has this triangular shape, this mound shape, this bell shape, this sometimes called normal shape. Chebyshev's theorem makes no such assumption. Let's go ahead and state Chebyshev's theorem now, and then we're going to see how we can apply it in some applications here. We can say that for any set of data, either sample or population, and a constant k, where k is at least 1, at least p% of the data lies within k standard deviations of the mean, where k and p are related with this little equation here. The percentage p is equal to 1 minus 1 over k squared, where k is the number of standard deviations the data lies away from the mean. Now, to compute that number of standard deviations, k, we got some formulas for that, and we'll take a look at them here. Now, let's take a look first at the graphical form of Chebyshev's theorem. Here, I just kind of drew a wacky dispersion here, distribution here. Has no rhyme or reason to it. It's definitely not mound shaped, not triangular. And here's what Chebyshev's theorem says. Now, I use population parameters here, but the same thing applies to sample statistics. Here's the mean, and here's the interval A and B. Here's the left endpoint A, right endpoint B. So the number of standard deviations k to the left endpoint is mu minus k times the standard deviation. The right endpoint B is mu plus k times the standard deviation. This theorem tells us that at least p% of the data lies in between A and B, where p equals 1 minus 1 over k squared. So like I said, it's kind of a weak form of the empirical rule. Let me show you what I mean here too. Let's make a few observations first, and then we'll take a look at, kind of compare and contrast the empirical rule and Chebyshev's theorem. So first, in order to apply Chebyshev's theorem, the k value has to be 1. In other words, the values of a and b we just saw in that graph have to be at least one standard deviation value away from the mean. In other words, distant from the mean. Now, one thing that's to our advantage here, in order to apply Chebyshev's theorem, a and b have to be the same distance from the mean. All right, so you have to go back k times s to get to a, and forward k times s to get to b. All right, so that really kind of helps us do some computation. We can say that for an interval of values a, b, and the number of standard deviations, that number k is given by, look, we have a little something that kind of looks like a z-score, only we'll call it a k-score. So what is it here? It's the right endpoint b minus the mean divided by the standard deviation. That gives us k, the number of standard deviations that the value b lies away from the mean. So we compute the distance, b minus a, divided by the standard deviation. Same thing is true for a sample. The formula is the same, but we're just using sample statistics here, x bar and s. So that's great. We don't have to worry about a, because remember, in order to apply this theorem, a and b have to be equidistant from the mean. So without loss of generality, we'll use the right endpoint. K will always be a positive number. Now, in terms of computation, let's take a look at some common values for k and what they mean in terms of interpreting the result. First, let's say the k value is 1.5. All right, that means the p-value is 0.56. Now let me show you how I get that. Let me grab a calculator here. I've got this scientific calculator. What's nice about it does math print. I'll just hit this fraction key here. Put in the fraction 1.5, 1 over 1.5, pardon me, and then square that using the x squared key. So we get 5/9, or in decimal form, 56%, rounded to the 2 decimal places. So that means about at least 56% of the data lies within 1.5 standard deviations of the mean. If k is 2, what do we get there? 1 minus 1 over 2 squared. That's 1 minus 1/4, or 3/4. So at least 75% of the data lies within 2 standard deviations of the mean. Now, we're saying at least 75% because it could be more, and quite often is, depending on how the data is distributed. But this is the least we can say. For 2.5 standard deviations away from the mean, that's at least 84% of the data values are encompassed between 2.5 standard deviations of the mean. When we get up to 3 and 4, what do we get there? 8/9, or 89% of the data. If we go way out to 4 standard deviations, that's a long way. That means at least 94% of the data lies within 4 standard deviations of the mean. All right, in terms of what those data values are. All right, so let's start to take a look at some applications. Now there's 2 types of applications. Some books have one type, some books have another, some have both. We're going to cover both types here, so we all know what to do. The first type is when we are given an interval AB and we want to find the percentage P for that. All right. In this case, the mean and standard deviation values have to be given to us. The interval of values A and B also has to be given. All right, so we have to be given those 4 numbers: the mean, the standard deviation, the left endpoint A, and the right endpoint B. Here's how we solve these. First, determine the number of standard deviations K is from the mean in this interval by computing. What do we got here? K. Now, notice here I wrote that K score formula in words this time. Take the right endpoint B minus the mean, that could be mu or x bar, divide that by the standard deviation. All right, that'll give us the numerator is the distance, divide by the standard deviation, that gives the number of standard deviations. The data value, the right endpoint, lies away from the mean. So we have K. Step 2. use the k value to determine the proportion or percentage using our equation from Chebyshev's theorem here. P equals 1 minus 1 over k squared. Cool. And then we want to write P as a percentage. The answer will always be a proper fraction here by definition. And then interpret the solution. And it will always include a phrase kind of like this. At least P% of the data values lie anywhere from A to B, where P is the percentage we compute, A and B are those endpoints we are given. So, having said that, let's go ahead and launch into an example. That's how we learn best. In 2011, the federal minimum wage was $7.25. For the 50 states and the District of Columbia, the mean of the state's minimum wages is $6.51. The standard deviation, $2.39. All right. Now the distribution of the minimum wages is negatively skewed. Now I have a histogram of that data, so let me get that up here so you can look at it. There it is. So notice here, the data is skewed to the left. It tails off to the left. All right, because most of the data is right here at 725. Most states have exactly the same minimum wage as the federal government does. Some have a little bit higher, and 5 of them have no state minimum wage at all. And so some of them have lower values. All right, so notice here the data is not triangular. It's not mound shaped. It's skewed left, negatively skewed. All right, so here's our question now. According to Chebyshev's theorem, at least what percentage of the state's minimum wages are anywhere from $3.51 to $9.51? All right, let's get to work on the solution here. First, note that we are given the population mean, mu, population standard deviation, sigma, and an interval of values, A and B. In particular, A is $9.51. And we want to find the percentage for that P. All right? So we're given 4 values and we want to find P. So let's get at it here. First, we see that the right endpoint is $9.51. So let's go ahead and compute the K value. All right, so here I'll grab a graphing calculator this time. So what do we say we want to do? We want to take the right endpoint, $9.51, subtract off the mean, that's $6.51, and then divide that number by the standard deviation, $2.39. All right, so there we go. So it looks like rounded to 2 decimal places, that would be what, 1.26? So what are we saying here? That right endpoint and the left endpoint are each 1.26 standard deviations away from the mean. All right? So what do we do with that? Oh yeah, we want to find the percentage now, the value of P. So we found the value of K, computing the K score, so to speak. So the value of P, there it is. All we did was we took that number, 1.26, plugged it into our formula there, 1 minus 1 over K squared. All right? And so here, let me just verify that on my calculator here. 1 minus 1 over 1.26, and then we want to square that. So there you go, about 37% rounded to 2 decimal places. So there we go, we found the percentage. Now let's go ahead and interpret the solution in terms of the problem situation here. So this means that at least 37% of the states have minimum wages anywhere from $6.48 to, I guess that number was $9.51 right there. All right. So notice here, we're talking about 37% of the states, not 37 states, and it could be more, and probably is. If we had the exact data values, we could find out. All right, so that's the first type, where we're trying to find the percentage. All right, now the second type here is a little bit, it's kind of turning that application on its head. Find the interval of values, A and B, for a given percentage, P. So in this case, the mean and standard deviation values have to be given to us, and the percentage or proportion P also has to be given. So to solve these, first we use the given p-value to determine k. In other words, the number of standard deviations A and B lie away from the mean. So in other words, we have some algebra to do. Take this equation, solve it not for p, that's going to be a number. We have to solve it for k. That's okay. I mean, we've done a lot of algebra, so we'll be able to handle that. So once we find k, we have to find a and b. So the left endpoint a is found by taking the mean and subtracting off k times the standard deviation. There it is right there. So left endpoint, we want to take the mean and subtract the k value times the given standard deviation value. For the right endpoint, same sort of deal, only we add on k times the standard deviation. So we take the mean, add on k standard deviations, that gives us the right endpoint of our interval A and B. All right, so let's take a look at an example of this one now. A sample of CEOs from California had a mean annual salary of $5.4 million and a standard deviation of $1.8 million. All right, so there's some data for California CEOs. According to Chebyshev's theorem, what is the interval in at least 80% of the California CEO salaries lie? In other words, what range, I use the term range in the sense of the English language, not in terms of a measure of dispersion. What's the minimum and maximum value for an interval we can write that will encompass at least 80% of the California CEO salaries? That's what we're looking to find here. All right, so let's get solving this now. First, let's understand what we have to do. Here we are given a sample mean. Now, we know that because it said in the problem, it said a sample of chief executive officers. So that's how we know we have a sample mean and a sample standard deviation. And we were given the percentage, 80%. So we need to compute the values of A and B for the interval, that open interval A and B that we have. So in order to get these values, we must first find K, the number of standard deviations that they lie away from the mean based on the percentage P. All right, so let's get at it. First, to get the value of K, we first note that 80% is 80 over 100, or just 4/5 as a fraction. Now we got to do some equation solving. So we need to solve the equation P equals 1 minus 1 over K squared. Solve that for K. There's the equation right there. 4/5 equals 1 minus 1 over K squared. This is about the hardest algebra you have to do in introductory statistics, so don't worry about it. That's what we're given here. Now, think of what we want to do first. This says minus here, and we're trying to solve for K, so let's just transpose this term over to the left, all right, and make it 1 over K squared. And let's just take this constant 4/5, transpose it over to the right, and rewrite the right side as 1 minus 4/5. All right, so there we have it so far. Now, let's go ahead and simplify the right-hand side now. Let me grab that scientific calculator I was using earlier. 1 minus, make a fraction now, 4/5. You guys can probably do this in your head. So we get 1/5 for that, don't we? All right, 1 minus 4/5, 1/5. So there it is right there. And now, let's see, we're trying to find K here, right? But we have K squared. So notice what we can do is just kind of cross multiply to get rid of these fractions. K squared times 1 is K squared. 1 times 5 is 5. K squared times 1 is K squared. 1 times 5 is 5. So by just cross multiplying, we get K squared equals 5. Now it's just a matter of finding the square root here, right? Notice here, we just need the principal root, in other words, the positive answer. And the reason for that being is that, the K has to be at least 1. So let me go ahead, and if you don't mind, I'll go ahead and stick with this scientific calculator here. So I'll hit the square root key, put in a 5, and then change that to decimal form. Looks like what? About 2.3 2.34 rounded to 2 decimal places. All right. So here we go. Let me look at that number. 2.24. Pardon me. There it is. 2.24. There we go. Okay. So what are we saying here? 80% of the data lies within 2.24 standard deviations of the mean. So, oh, look, I just said that. Okay, now let's go ahead and find the left endpoint. So what do we say we want to do here? We want to get the left endpoint, and I'll go back to that graphic calculator for that one. We want to take the mean, 5.4, and then subtract the number of standard deviations, 2.24, that's k, and then multiply that by the standard deviation of 1.8. There we go. So what do we get there? About 1.37 if you want to round that to 2 decimal places. All right. So there it is. X bar minus KS. Remember, using sample statistics here. All right. So we get 1.37. Now, for the right endpoint, we want to add on. We want to go to the right 2.24 standard deviations. Here, I'll stick with my graphing calculator here. Now I want to get this last expression. I just want to put a plus sign there. So I just hit the second key and enter, and then just scroll back here. Make that subtraction sign and addition sign. There we go. 9.43 rounded to 2 decimal places. There it is. So there's our right endpoint. All right. So there's A, there's B. That's what we were looking for, isn't it? So let's interpret the solution. So this means that at least 80% of the California CEO salaries lie anywhere from $1.43 to $9.47 million annually. So that's it. There it is. That's Chebyshev's theorem explained.